Hey folks, this is me, Vishwas, and I am the creator of this podcast. And basically, every single day, I love to speak with a lot of professionals, and I love to talk with a number of people from different institutions like Microsoft, Facebook, Twitter, Tesla, Uber, and things like that. So, here's the set of podcasts that I did with some folks, and also I would love to share my screen and share some of the insights about the world of GANs. And GANs have been such a provocative topic in my entire life because lately I just realized one thing, that it's not complex, but yet we are having some sort of a misunderstanding and understanding it. And this is just a quick intro with respect to the code, with respect to the data set, with respect to everything that we are talking about. But I just took some well-known data sets like fashion MNIST and MNIST because everybody gets to know what is there inside that data set so easily that you need not have to worry about what's happening, and everything is sorted there. And thank you so much to Usha ma'am for giving this chance, for giving me this talk. And this talk means a lot to me because I have been working on this for a while, and I would love to share my knowledge over here and just get some more work done for understanding, okay, this is what I need to be doing, and this is what I need to be thinking about. And yeah, everything is there, but what's next? So thinking of what's a training data is always going to be some sort of a quick introduction, something like, okay, you have some set of data sets which are already being tuned for training model, and how do we use that, train a model, extract some insights, and utilize it for some more data sets which are unknown and which are away from what training data set was. So test set should never be equivalent to the training set. That means none of them should be repeating. And GANs have a problem statement, which is like what to sample from complex high dimensional training distribution. There is no direct way to this. It's deep illusion of the deep learning that is taken as math, which is something like, okay, you have a set of dreams and how to achieve it. So now you know the path for this, but next what? So GANs have their own set of problem statements. And these problem statements, there is always a huge set of challenges which is always there. So the solution is sample from the simple distribution, example, random noise, learn transformation from the training distribution, and actionable to the reasonable analysis. That means that you have a set of code, you have a set of practices, then how do you evolve it? And the question is, when can we use the represent the complex transformation function, processing of the information with the quality of the experience? That means that I have a set of data set. How can I really create a new set of data sets? Like, can I add noise? How much noise should be added? What noise? What should be the transformations? What should be the pre-processing? And what should be the entire flow of this entire architecture? So if you can think of, he's one of the creators of GANs, and he actually named GANs, by the way, is Ian Goodfellow. Ian Goodfellow is one of the most influential people, and I think probably he has seen deep learning from the age of Theanos, Kefi, TensorFlow, whatnot. And he was previously in Google, now he's in Apple, and just waiting for some new disruptions from his side. And this is a podcast with Lex Friedman, one of my favorite engineers in the world of AI. He dreams to build a robot like the gold standard, and yes, he's going to build, and he's working mostly in the self-driving car domain. And Ian Goodfellow is an amazing person, if you can think about. And there's a lot that goes behind building such kind of architecture. So essentially, there is plenty amount of flavors of GANs which are already being existed, which is like, okay, there is an existence of this architecture and that architecture, and what's the essential part of using all of it. So this is what we are talking about. This is what every single AI architecture is built towards. And in a meanwhile, when you think of such kind of an architecture, you can think of something like you just have some set of an architecture which is already required, and you just have to just get some move. And basically this is what is happening behind the AI system. And when you think of some sort of an application which is already built, and there is always a need for such kind of an application, there is always that end goal that we are always thinking about. So right now, there is always a simple need for your system to grow, system to analyze and whatnot. So basically, batch normalization is always there. Leaky reduce activation layer is always there. Convolution layers are always being existed in the discriminator layers and so on. So as you saw, GAN's architecture have generators and discriminators. Here we are just giving an architectural overview of it. And how training happens is basically the way in which all the architecture has been working and so on. So targets are sampled out. There is always a generator network. There's always a discriminator network. And to be very frank, you can just go back and look at this sort of an one pager for your Jensen-Shannon inequality, and everything is sorted. And this is the generated result that I just got from the MNIST data set. It evolved from that. And at the end, there is a noise there, which is because I just used 5 epochs and nothing started to work. And that noise is basically just to say that, okay, if I had trained a little bit more, it would have really given me a new set of data set. Like, just see, this is now evolving. This is now evolving. And even if you look at the 0 is also evolving. And there is a set of data set. There is a set of 3, which is evolving to 0, 9, which is evolving to 4, 6, which is evolving to 5, and 8, and so on. So a simple example is like you can take Celebi data set, but I would always suggest you guys to always get inside some sort of an deep face generation and simple smiling image and neutral woman and the neutral man. And there's always a neutral woman and a neutral man, which is always equal to a smiling woman. And this is how you start building some sort of an architecture. And this is how you start training towards GANs, and GANs are always there. So there's a glassed man. There is always some sort of an image which is always a need for generation. So if somebody asks you how many trials did your GANs architecture go through in order to give proper result, it's probably sometimes infinite. Sometimes some architectures won't even give results so easily. Sometimes it's like gazillion amount of time is required and so on. So this is what I call about an epoch, which just ended off with, I think I just did 5 epochs initially, and I think 10 epochs was what being shown. And this is the result of the image that we are talking today. And the generation is always going on. And sorry for my 5 epochs that I did. I'm just lazy to train for a very longer time. And GANs for the fashion MNIST, I just did only 5 epochs and it started working and so on. So lately, when you think of all these architecture, it's going to evolve. And this is actually 2 epochs. It's actually generating some sort of an image like this. That means I just stopped the training process. I didn't stop the training process. It was training, but the generated images were this. And the 5th epoch, it's actually 3rd epoch. This is the 5th epoch that I'm talking about. And at the 10th epoch, at least there is a visible change. Probably if I had given some more epochs, it would have trained much more quicker. But as always, I'm so lazy. It's actually 11th epoch that actually is being done here. So let's just jump onto the code and let's just demystify what is there. So let's just go to the GIF generator from the TF GANs. So I'm using, it's already run and it's already saved, and I'll be sharing you guys the notebooks. So as always, TensorFlow 2.7.0 is always there in the Google Collaborator. And what we just did was we just started using the same old data set from the MNest and it's being loaded. And there is a training model which is given there. So let's just see what is the buffer size, which is say buffer size is nothing but, okay, there is 60,000 set of data sets and each of the batch sizes that is going to be trained onto a neural network is 256. If your batch sizes increases, the momentum is going to be less, and also the loss functions are going to be extremely higher, and that means that your learning parameters decreases. So always try to keep your batch sizes up, buffer sizes up, because they are just going to have a huge impact on your entire architecture that you're talking today. And this is always the prerequisite code that we always talk towards. And there's a training data set, and that training data set was being evolving. And now we just split into train test, and that's always X-train, X-test, Y-train, Y-test. And X-train, Y-train will always be like X-train will be the data set, Y-train will be the annotations that will be going through. And it's all being optimized. It's always there. These set of prerequisites code is always there on the internet, and you can go and check out what is there with this entire architecture that we are talking about. And as usual, I use a sequential model in order to analyze, okay, this is what we require. And let me just share my entire screen so that everything is visible. And let me just go to the whiteboard. I think this should give you a quick introduction about every little thing that we're talking here. So I do a lot of sketches from on my GitHub, or not on my GitHub, it's on LinkedIn, so you guys can check out. And let's just go on. So what's a sequential net that we are talking about, and what is it all about today? So sequential. So a sequential is one after one after one. So your neural network will just get stacked up like this. And there is always a training which always goes down. And then here I have not trained the parameters over anything, and you are just thinking about what can be learned from here. And your sequential is just a beginning step which says this has to be your approach. And adding layers, what we did was we wanted a convolution layer. So what we did was there is a 7 cross 7 cross 256. Think about it. The batch size is 256. So right now, what you have is a layer which has a dense layer, which is 7 cross 7 cross 256. That means every layer is just now starting to get the inputs in this form factor. And the input shape is always 100, and it's basically a sort of a convolution neural network that you're designing towards. And that just goes deep and deep and deep, and you start learning. And assert statements are really bad when you are not in a production system. If you want to really understand what's a production system, just do a lot of assert and just imagine, okay, this is what is happening. Assert just gives you a set of outputs which are required, and all of these are functions that we are talking about, requires a lot of assert statements inside it. So we are now doing that. So it's very simple. What we did was we just call the same old model function through this parameter here. And there's a noise which is always generated, and the noise is being plotted here. And the generated image will have an addition towards it. And your CMAP, the color mapping is always to the gray. You can do for a BGR, but I would never suggest that. Just go for the gray because it gives you a lot of insights, because in your neural network, there is always a new way in which you can start working towards an AI system that is always there. So this is how the system goes and starts working, and AI is always building. And to make a discriminator model, there is always a thought for, okay, now we have a generator. Let's just design a discriminator and start working towards all the set of codes that we have. And later on, we just call the discriminator, and now we get a tensor weight of this. And trust me, int is going to be so heavy, but your float is not that heavy on your neural network. And this is some sort of an undesired change. Like, I'll just show you how. Float 32 versus int 32. So now there is a set of possibilities that we are thinking about. There's a set of compute layers that we are talking about, and I will make sure that this will be there in the slides as well. So this is going to the slides, and where is that? My podcast, of course, it will go for the slides because I want you guys to hear that. And the Jensen Shannons is always there in the speaker note of this entire presentation. So make sure that you learn that. And also there is a set of references that I've already given here. So if you think of Ogly is actually from Facebook research. Facebook has been doing pretty amazing in terms of the research that they are bringing in for all the things that we are talking here and so on. So please do refer that, and also some set of papers here. I always refer to this, and make sure that you get to know, okay, this is what discriminator, the total loss has been generated, and so on. And so the fake outputs are always given out. So, the magic of TF function is that, you can draw any sort of sessions, and you really need not have to do a session like this. So what I'm showing here is a kind of a session that we just wanted to run, like just wanted to see how big of a data set can happen for the TPUs and the GPUs, but tf.function is always there for you to help at tf.function. It's always here. So you guys can go for all the set of practices that is always there. It's always a good practice to add a function in. So instead of making sessions is always very bad. And this is what we are talking about. And at the end, I got this result, and this is a GIF that I showed here. Where is the result? It's here. So it's a shabby one. So don't mistake me. It's just $5. There's that epoch is 5, and the noise dimensionality is 100 because above I've given 100, and the number of examples for the generators is 16. It's 4x4. If you want, change this to 20, and you can run all. And just ask for the reconnect, just reconnect, run all, everything will start working. By the time we finish something called as probably it will come out as 5x4. Let's see, 4x5 or 5x4, whatever might be the dimension of it. So let's just run all of it, and everything is sorted and everything will be done. So docs is always required, and if you want, you can use something called as git books, and everything is sorted. So this is always about the session that we are talking about. So pip install TensorFlow nightly preview 2.0.0. Instead, you can also do something like pip -- force install, and the version of this, it will start working. But I just wanted to show how to programmatically do this, and I just did that. So as soon as we import TensorFlow, there is always a nightly version which is always required. But I just do the same old way and the same old dimension of all the codes that we are talking here, and we are just taking in the data set, and we just looking at the model. We are now doing the same old generator and a discriminator model that is always there. Since this is always a defined neural network, tf.keras.model is always generated. And if you think of all the losses, there are logit losses, xgen losses, so it's discriminator real losses, discriminator fake losses, discrimination losses, gen losses, and so on. And at tf function is always used here because we are now in the era of 2.0. So make sure that you know what to be used. Oh, I feel it's not burden here. All right, it still used what happened. Oh, I think I got to know that. Okay, it requires 16 examples only, so can't help that. All right, so if I just do that, oh, it didn't work out because if you see the previous error, it was like lesser than or greater than 17, so it's always that. And now this will start working, and there will be a generation of a new set of GANs and the images, so on. So the trained images will always be there, and there will be an image which will come out here, the same set of image, because I have done 5 epochs. Probably a different result might appear, but let's see. Why did the execution fail? Oh, it still use the 20 version, so fine, that's perfect. So it will be available here on the later part. So let's just not think about that. So let's just think about this code. So this code is evolving right now. So n number of epochs is already considered as 11, and it shows out to be 10. And all the model.train parameters are called here, and it's being available here. So if you can think of any sort of an application which is always there, number of epochs is already done, and there's a shabby set of an image which is already generated. Probably the GIF is going to be much more worse here. Let me just stop it. Let me just see what is happening here. All right, I just did a keyboard interrupt, and let's see what's the embedded. Oh, since it only had 1 epoch done, and it now generated a shabby image which is not even equivalent to any of the numbers. But probably what you can do is you can use some sort of a data set, and you can start delivering something as textures here. Textures also work the same. And so that's it, folks. Thank you so much, and do enjoy the session and the conference which is going on. So thank you so much, folks. Thank you, and bye-bye.